Ah, the Lemon point is the isotomic conjugate of G. No, it is the isogonal conjugate of G. I mean, these two are the same thing. It's just another name for it. Isogonal. Because you can't take but the isotomic conjugate of the centroid is itself. Like if you take this, reflect across the midpoint, it's still this. So the isotomic conjugate of G is G, but the isogonal conjugate of G is K. Yeah. So let's look at a few properties of this because it's quite interesting. So first of all, there's one way that you can construct it, which is by doing this. If you draw the circumcircle like that, then you draw two tangents, right? Then it turns out that this line and the median, they are isogonal. So let's try to prove this. Let's try to prove this. Basically, you want to prove this angle is equal to this angle. Lemma. Uh, okay, how would you use that lemma if you want to use that lemma? Well, we're trying to prove this. We're trying to prove that these two are the same. M is the midpoint of BC, yeah. There are a few ways to prove this. The uh you can use you can bash it out as well. But on which triangle? BM, MC. Okay. So if you use that, then yeah, okay. So you get the angles. Then how do you relate it to the to P? P perpendicular to BC. Let M prime be the point such that the angle controls. Try to prove that M is the midpoint. Yeah, that's one of the way. Yeah, that's one of the ways. Uh, right. Let's see. We can also use this previous thing that we used. CMBM is sine BF, sine BAX, sine C, sine CAX. Okay, what's X over here? Is your X P? Yeah, yeah, cool. Yeah, so mm, which resource? Well, I'm not using any resource now, but like uh, most of the things you can find in AGMO if you have the book. But yeah, this is a it's a very well known lemma over here. So you can try and see, okay, you make a point X over here. Like these two lines. Right. So then we have, let's say this is Y. So if we manage to prove that Vy over Yc, because from the previous lemma, for isogonal conjugates, you have this relation, right? So you want to prove that Vy over Yc is equal to AB over AC squared, right? Or let's just make everything simpler. You want it to be equal to C over B squared. Hmm. So how do you find By over Yc? One way to use this using harmonic quadrilaterals, but let's not use it here because AB x C is actually harmonic. Never mind. So By over By over Yc, Y over. So we can use, let's say, mm, look at this one over here, PB over BX. This will be equal to PA over PA over C, right? And then similarly, if you look at the other triangle over here, we have we have PC over CX equals PA over B. So there's a lot of things that are equal right here because like these two are the same and these two are the same and CX. Yeah, so if we divide it, we can get that BX over CX is equal to BX over CX is equal to C over B. Right. So that means what? That means the ratio of these two lengths is the same as the ratio of these two lengths. This is in fact the definition of a harmonic quadrilateral. But now you want By and you want Yc. But then you can use similar triangles within the cyclic quadrilateral. So we can say, okay, uh, By over AB is the same as xy y over yp same as y over cx. And then cy over ac the same as y over ac x y cy over yc xy over bx. Okay, so that means by over yc is ab over cx times bx over ac. Bx over cx is c over b, ab over ac is c over b. So that's c over b squared. So you can bash the ratios out. Because there are a lot of similar triangle here, similar triangles here. So of course, once you do this, you can kind of simplify it to one sentence if you want, one equation. But you want to get information from the diagram, you just try as many ratios as you can, try to simplify them. Okay. Yeah, so this tells us there's a new way to construct the C-median point, which is to just, well, take this triangle formed by the tangents, right? Formed by the tangents, and then connect the lines. Then you get okay. Right. So yeah. Any questions here? No. If not, then right. If not, then we can look at something new. Look at something new. So now that we've learned so many centers, C-medians, in-center, X-center, and so on, those properties, let's introduce something new right here, which I'm not sure how many of you have learned this before, but it's one of the cool way of bashing, which is barycentric. Because it's quite a nice coordinate system that you can use to solve a few problems. And yeah, so let's try to introduce it uh for everyone here. Okay, so I will start off with the basics first. I'll start from scratch, right? So we have to start from a little bit of vector geometry first. Okay, so in the 2D plane, right? If you have a point A, let's say you fix an origin, right? You fix an origin. That means any for any point A, I would call the position vector of A, denoted by this arrow on top of A, is just the vector OA, right? So if A is here and B is here, Then we have two vectors, vector A, vector B. So now, what are the position vectors of the points on the line AB? So it could be anywhere here, could be anywhere here, could be anywhere here. So what are these points? How can we parameterize these points? So let's say X. So what's X? Any point on the line. Yeah, it will be a linear combination of A and B. In fact, a very special linear combination. So let's kind of derive it right here. Uh, so X here, which is OX, by the way, it's gonna be OA plus AX, right? But AX is some multiple of AB, right? Because they're parallel, right? That's the crucial point that we're making here. So this A plus lambda B minus A, which is 1 minus lambda A plus lambda B, right? So, so what's X? X should be a linear, yes, it's a vector. X should be a linear combination of A and B, but the coefficients must add up to 1. Right? Make sense? If I draw a vector arrow on top of a point, it means the position vector. So it means, uh, for now, it means the vector from O to that point. Why OX is OA plus AX? That's like the how you work with vectors. So so vectors, one way you can see it is by looking at how you like you can add the checkpoints in between. Oh. Okay, so vectors is basically okay in the simplest sense, you can write vectors as a coordinate, for example. Let's say so 1, 2 would be the vector from in the x direction 1 unit, in the y direction 2 units. So this is the vector. And you can add things like let's say 2 plus 2, 1, they'll be adding like this. So you get 3, 3, which is this vector. So it's basically two-dimensional addition. You go from one point to another. Right? So yeah. So that's like the R squared formation of vectors. So anyway, lambda is like a coefficient over here. So because if you have two vectors that are parallel, one is going to be some factor of the other. Like for this case, it's around 2 times the first vector. So the vector x over here, you can do some manipulations, and you can see it will be a linear combination of A and B. Right? Is this okay? Right. So that means, well, because there are infinite, there are many positions x could uh be at, right? So for each lambda, there will be a position for x, and for each position of x, there will be a certain lambda. Make sense? Cool. So now, if you look at this relation, this is independent of O. So O could be anywhere on the plane. But this thing would still hold, right? Make sense? This thing would still hold. Now, instead of looking at a line, let's say we're in a 3D space. So this is a 2D plane. And now we have 3 points on the plane. And then we have a point, let's say O is on top here. And now I want to ask the same question. The question is, how do you write points that are on the plane ABC? Because for a line, you need 2 points, and then you get the whole line. For a plane, you need 3 points, and you get the whole plane. You need 3 different points. So yeah, it will be again, a linear combination of A, B, and C, but is there any additional constraint that we have to impose on X, Y, and Z? So yeah, so we can write this as, well, one way of doing it is, I mean, you can kind of say we can write OX to be, let's pick a point, right? Let's say OA plus AX, right? Now, AX is a vector on the plane. And we know that if you have two vectors of different directions, right, we can get any mixture of them that will get us to any place on the plane. Make sense? Make sense? Like if we have one vector here, we can go anywhere on the plane. For example, if you want to go here, then we just go, okay, we multiply this vector by minus 1.5, and then we add this. Or if you want to come here, we can go this and then go up here. So it's always a mixture of those two different vectors. So we can always write AX as a linear combination of, let's say, AB and BC. Like AB or AB and AC, doesn't really matter. But let's put everything in terms of like with respect to A. So if you expand this, it's B minus A plus lambda C minus A. Well, we can get 1 minus mu minus A lambda A plus mu B plus lambda C. So again, it will be a linear combination of A, B, and C, where the three numbers add up to 1. Right? So again, this is independent of O. O doesn't have to be anywhere. O could be on the plane. O could be away from the plane. This relation will still hold for the same numbers of alpha, beta, and gamma. Right? So now imagine that this is our Euclidean plane. This is our Euclidean plane. So we have A, B, and C chosen. Then any other point X can be written as a linear combination of A, B, and C with those three numbers adding up to 1. And so this number, this triple, will be the coordinates, the barycentric coordinates of X. Means every number has now every point on the plane has now three numbers associated to it: alpha, beta, and gamma. Okay. So let's look at a few points. Let's say we fix A, B, and C already. So again, this coordinate depends on where you choose A, B, and C. It's kind of like the origin of this coordinate system. Instead, there are like three origins. There's A, B, and C. Assuming we are having the barycentric coordinates with respect to these 3 points, what's the coordinate of A? So we just ask ourselves, the vector A, the origin, it doesn't have to be the circumcenter, it could be anywhere. It could be anywhere on the plane, it doesn't really matter. We just write, yeah. So we ask ourselves which numbers, alpha, beta, and gamma, can we write it such that A equals this, where alpha plus beta plus gamma is 1. And of course, there's only one, well, there's one obvious way, which is 1, 0, 0, right? 1 times A plus 0 times B plus 0 times C. So the coordinates of A is 1, 0, 0. And similarly, the coordinates of B is 0, 1, 0. Coordinates of C is 0, 0, 1. Makes sense? Now, for example, let's say we have the midpoint of BC. The midpoint of BC. Then how do we write M as a linear combination of A, B, and C? Right? So if you've familiar with vectors, if you have one vector here, one vector here, and we want the midpoint, let's say we take the midpoint of the endpoints, this vector would be uh delta. Oh wait, yeah, alpha, beta, gamma. This vector, let's say this x, this is y. This vector is x plus y over 2. You can write it. You can prove it by saying OB is OA plus B, OA plus AC, AB, and OA plus half AC. Right. Am I probably going too fast? Right? Uh, it's if you haven't learned vectors, this might be a bit hard to follow. Okay. So OB, OA plus AB, and then AB, in this case, if it's the midpoint, AB is half of AC. And if you have AC, this just means it's OC minus OA. So it's OA plus OB over 2, or OC over 2. So that's how you can find the midpoint if you have two vectors. So that means M is actually, in fact, B plus C over 2. Right? Imagine O is anywhere. Let's say it's best to think of O as being away from the plane in the third dimension. Then M is gonna be like OB plus OC over 2. So the coefficient is 0, half, half. So M has coordinates 0, half, half. It's okay. Right? In fact, uh, let's just focus more on vectors first, just for people who what new to this. So think of a vector as going from one point to another point. So this is the vector AB. So it has a direction associated to it. But whenever you have two vectors, if you add them, like let's say another vector like this. So the notion of a vector has nothing to do with the position of where the vector is. Like if they have the same length and the same direction, they are considered the same vector. Right? So if it's C is D, and let's say they're parallel and they have same lengths, they have the same length. And these two vectors AB and CD are the same vector. Oops, sorry. Yeah, wait. Detour vectors. So when you add two vectors, let's say you have x, y being like this, you basically put one vector on top of the other, and then you just declare this as the new vector. So if it's u, this is v, this is u plus v. Right? And if you want to flip the direction, you just multiply by minus 1. So this is minus xy. In fact, y-axis is just minus xy. It's kind of like signed lengths, but now you can go in any direction instead of along one direction. So when we have, let's say, one vector like this, and another vector like this, just now we've shown how to find the vector that goes to the midpoint of those two endpoints, right? Let's say I just want to divide it into, let's say, m by n. Let's say I give an example, 1 to 2, the ratio 1 to 2. Then how do we find this vector? Then this vector over here, well, we can say, all right, we can let this be A, B, C, and O. It'll be OB. So how can I walk to OB? I can walk to A first, and then walk to and then walk to B. Okay, A is something that we like already. We want to write X in terms of U and V, right? We can call it U right now. Doesn't really matter. Yeah, exactly. And AB is okay. AB is not BC. AB is BC over 2, but let's write it in terms of something that has nothing to do with B. Yeah. So AB is equal to BC over 2, but we don't want the B to appear. So we can write AB as 1/3 of AC. Then you can actually write this in terms of U and V. Because now, what's AC? And the shortcut is if you just take the final one minus the initial one. So that'll be that'll be V minus U. And well, the real reason is just that you have to flip U, then you follow V. So it's like minus U plus V. So it's basically V minus U. So you get 2/3 U plus 1/3 V. So again, you get two coefficients that add up to 1, which makes sense with our first discussion just now. Right? Okay. So in fact, now you can also find the the centroid of a triangle just by asking, okay, is the midpoint M? No. What is on the on this thing on this line AM? So yeah, you would yeah. So in the end, it must be something symmetric, like one third, one third, one third. So let's see how we can get that. So we just now we found that M is 0, 1, 1 because it's oh sorry 0 half half because it's half B plus half C. Well, AM this is 2 to 1, right? So we can find that G is in fact 2/3 of M plus 1/3 of A. Because it's a 2 to 1 ratio. A quick way to remember which one goes to which coefficient is that the closer one must have a larger number. The closer one must have a larger number because it has more weightage, right? It's like a weighted average. And then the one with the larger weight will be weighed more, will be more prioritized, will be closer to that point. You can think of it this way. So, and then this is, 0 half half plus 1/3, 1 0 0. So this is just 1/3, 1/3, 1/3. It's nice because now it's symmetric everywhere. Right? Yeah, you can, yeah. So I'll talk about the aerial definition afterwards. Mhm. Is this so far so good? Yeah, in fact we can talk about the aerial definition right now. So another formulation of how we can find those three numbers, alpha, beta, and gamma, is by looking at areas. How do I find these three numbers? Okay, in fact, before that, let's talk about projection first. Let's say x is here with this coordinate. Let's say we draw ax, and this becomes a1. Yeah, so this becomes a1. Then what's a1? What's the coordinate of a1? If this coordinate is alpha, beta, gamma. Yeah, I'll come to the aerial definition afterwards because I have to prove that they are equivalent, right? We cannot just take two different definitions. So let's see. A1 lies on AX. So again, it's going to be a linear combination of A and X with coefficients adding up to 1, right? So A1 is going to be something times A, something times A, let's say something times A plus something times X, but it must add up to 1. So 1 minus lambda times A, 1 0 0 plus lambda A, lambda B, lambda, gamma. That'll be this. For some lambda. On the other hand, A1 lies on BC. So A1 has got to be a linear combination of B and C. So this thing, which is the coefficient of vector A, must be 0. Right? So lambda is 1 over 1 minus alpha. Which then you can plug it in and get A1 is beta over 1 minus alpha. And then, oh, sorry, it's 0 first. 0 beta over 1 minus alpha. Gamma over 1 minus alpha. Or since alpha plus beta plus gamma is 1, this is just this. So if alpha, beta, and gamma gets projected onto the opposite side, the new coordinate is this, which first of all makes sense because the three numbers add up to 1. 0 plus beta over beta plus gamma over beta plus gamma is equal to 1. Okay. Now, this motivates something nice, which is something called you want to homogenize a coordinate. For example, if we have like in fractions, for example, 2/3 will be the same as 4/6, right? Because I kind of scale 2 and 3 by a certain constant. We're going to do something similar here. We are going to say that alpha, beta, and gamma, and let's say something else, C alpha, C beta, C gamma. We're going to treat them as equivalent as long as this C is non-zero. So then we can simplify our notation. Because if you think about it, we want we want the three numbers to add up to 1. So it doesn't matter, you don't really have to write out all three numbers. You just have to write out 2 and you can infer the third one. Or another way is you can scale all the three numbers to some nice triple. And whenever you get that data, you can infer what the original three numbers were because you just have to scale them so that they add up to 1. So that means we can treat this as the same as 0 beta gamma since it's just a different, it's the same scale. And now that it doesn't add up to 1, we can just add 2 colons instead of commas in order to just say that this is a ratio, this is not like the actual three numbers. Yeah, so this is what we call the unhomogenized form. So the conclusion here is that if you have a point alpha, beta, gamma, its projection onto BC is just 0 beta gamma. And similarly, if I connect it to the other side over here, let's say this A, this B, this C, then this will become alpha 0 gamma. And we connect it to C, this becomes alpha, beta, 0. So now we can solve, or you can already use this to solve uh the barycentric coordinates of a few points that we know. So for example, the in center, let's say, how do we find the coordinates of the in center? What are A, B, and C again? Good question. A, B, and C could be any three different points that are not collinear. Is whenever you fix A, B, and C, then you generate a new barycentric system where the coordinates of everything on the plane would depend on well, where A, B, and C are. So we can just pretend that A, B, and C are already fixed in place, and then calculate the coordinates of everything else. Right? So, but what we do know about the in-center is that whenever we project I onto the other side, it's gonna form this is C, this length is B. This ratio over here is also C to B. This ratio over here is C to B. Which means this point A1 is gonna be B over B plus C times B plus C over B plus C times C. Or in other words, this coordinate is gonna be 0, B, C. So A1 is this coordinate. But then you can say similarly, B1 is A0C, C1 is AB0. So by this property here, once you have these 3 points, we can infer what the middle point is. We can infer that the in-center must be A, B, C. Where here A, B, and C are the side lengths. We can also talk about the orthocenter. Let's see. Okay, before that, the area definition. So previously, alpha, beta, and gamma depended on the coefficients in this expression, which is already quite useful for most cases. But we can convert it into something that seems a little bit easier to compute, which is about areas. If this is A, this is B, this is C, and this is alpha, beta, gamma. This is 0, beta, gamma. Now, what's the ratio? Oops, sorry. What's the ratio between this and this. Let's see. Mm, let's keep the middle one as homogenized. So let's say they do add up to 1. Then x is d. X is alpha A plus beta B plus gamma C, which is alpha A plus some multiple of D, or some multiple of, yeah, some multiple of D, because we know that this is 1 over beta plus gamma. Oh wait, sorry. Beta plus gamma times D. Because D is beta, well, D is this. X is a linear combination of these two things, right? Which means it's just 1 minus alpha over here. So that means dx over dA is actually just alpha. Because now that your ratio is this ratio is telling us that this alpha is 1 minus alpha in terms of ratios. So dx is alpha times the whole length. But dx over dA, and this is just this is not barycentric, this is just this by areas. Dx over dA is just equal to the area of BXC over the area of ABC, or XBC, ABC, right? This is just by ratios of bases. The ratio of bases of the triangles is equal to ratios of the areas of the triangle. Okay, therefore, concluded, the barycentric coordinates of x, you can just, well, the first coordinate, you can just say it's this quantity, the area of XBC over the area of ABC, the whole thing. And then you can just find the other two by looping over yeah, the area is sign. So this is another way to find the 3 numbers. So for example, for centroid just now, we found it's one third, one third, one third. Let's try to use this again. Well, this thing is just 1/3 of the entire triangle. And same for the other two. So the area is 1/3, third, 1/3. So yeah, so that's another quick way to get the coordinates of a centroid. Right? So in this case, say I is a bit harder, but okay, I is also fine. So to get the coordinates of I, which we did just now, but now we're going to use the areas to find it. So BIC is A times R over 2. Right? R is is the in radius. R is the in radius. Sorry, IBC. So you can find out that if we draw three triangles like this, ICA, or like AIC, is now BR over 2, and ABI is CR over 2. So the ratios of these three parts is just A to B to C. So I don't care what they add up to. What I care is that the ratios of the areas, they are just A to B to C. So now we have I, we have G. So now we can find, for example, what O is. Well, we don't really need Conway, but Conway is just simplified notation. All right. So if you want to find O, well, in this case, we can take a look at what the areas, or the ratios of the areas of these three things are, right? So now all these three lengths is R, the circumradius. This is 2A. So OBC is half R squared sine 2A. You can find the other two as well, sine 2B and sine 2C, which means the circumcenter has coordinates sine 2A, sine 2B, sine 2C. This is like practice on how like to get comfortable with barycentric coordinates, because we haven't really talked about how we can connect lines, how we can solve problems with it yet. But once you are used used to these concepts, it will be quite a powerful tool. ABC is S times R, where S is the circumference. Yeah. You can, if you want to find the total area, just add these three up. So you get like A plus B plus C over 2 times R. So that's SR. So one thing to take note about this area formula is that we assume X is within the triangle in this case. So they're all positive. But when we move away from the triangle, some of the coordinates can become negative. So you have to take note of that. So this is actually what we call signed area, where we assign something is positive or negative. We keep a convention, which is, let's say, if we write it as counterclockwise, then it's always positive. Otherwise, it's negative. So like XBC is positive, ABC is positive. If X is outside here, then XBC is negative, ABC is still positive. Okay. Uh, yeah. Now we have I, we have G, we have O. Uh, let's see, we can. But H is still doable. It's just quite complicated. So okay, let's do H then. Well, I'll introduce it when we need to. So we can again use the area definition, which in this case we just have to find what these things are, right? A prime H, B prime H, and C prime H. So how do we find A prime H? And this is like, again, this is a synthetic geometry problem. How do we find A prime? Put this here. How do we find A prime H? So we can do angle tracing here. This is C, so this is also C, the angle. This is B. Okay, let's start off with BA prime first. BA prime is going to be AB times cosine of B. AB times the cosine of B. So it's actually just C cosine B. So this is C cosine B. Now we look at this triangle. Then we have A prime H is C cosine B divided by the tangent of C, which is C cosine B cosine C or sine C. You can use the sine rule if you want to simplify it. So it's 2R cos B cos C. So now we have a symmetric, we have a neat form for A prime H. Okay. Now, that would mean that the area HBC is going to be half times BC times 2R cos B cos C. So whatever it is, well, doesn't really matter because let's write it in a nice, because in the end we just want the ratios of the three triangles. We just want the ratios. So we can say this is proportional to A times cos B over cos C. Because the R doesn't really matter. Or we can even divide by cos A, cos B, cos C and say that this is just proportional to this. Oh yeah, sorry, yes, I okay, correct. Yeah. So now HBC is proportional to this. That means H now we can infer that it's A over, yeah, A over cosine A. B over cosine B. C over cosine C. See, but we can simplify this into something nicer because, again, remember the sine rule. A to B to C is same as sine A to sine B to sine C. So yes, so this is the same as tangent A, tangent B, tangent C. Cool. In this case, yeah. I mean, we're using a bit trigo bashing to find the coordinates of H. Yeah. Okay, let's now talk about more general points. Let's talk about isogonal conjugates and isotomal conjugates. Isotomic conjugates. So remember that if a point here has coordinate 0, beta, gamma, then the ratios of these two things is gamma by beta. So it's kind of always like flipped, which it kind of is kind of consistent from what I said, which is the one with the bigger number is the one closer. Okay. So what happens when I take the isogonal line? What would this new point be? Hmm. Well, there's a quick way of doing this. First of all, we use a lemma that we've learned, that lemma that we did. I mean, the homework we kind of did from the last class, which is the fact that is D is E, so BD over DC times BE over EC. This is C over B squared, right? Remember that? So that means BE over EC is just C squared over B squared times let me write this so to get something. Beta, this is gamma. DC squared, so beta squared over gamma squared. Yes. So E has coordinates. Copy that down. That's B squared, gamma squared, C squared, beta squared. Okay. Sorry, there's no square here. My bad. Square, square. Yes. So now, okay, let's just write this in a more symmetric way. I'm going to divide by beta gamma. So beta over B over beta, C squared over gamma. And now we're kind of done again because remember, if we have the three projections and they satisfy that relationship, now this is B squared over beta, C squared over gamma. Similarly, the other three would be, this one would be A squared over alpha, 0, C squared over gamma. This one would be A squared over alpha, B squared over beta, 0. So the isogonal conjugates point is going to be, just take the three things together, becomes A squared over alpha, B squared over beta, and then c squared over gamma. Yeah, so that's how you can guess the orthogonal conjugate. Which means if G is 111, which it is, then K, the median point, is going to be A squared over 1, B squared over 1, C squared over 1, which is going to be this. We can do the same for isotomic conjugates. Isotomic conjugates are way easier because now you just have to flip the ratio. So alpha, beta, gamma. I drop it here, becomes 0, beta, gamma. So the isotomic conjugate is just going to be 0, gamma, beta. Scale it so that it becomes symmetric. 1 over beta, 1 over gamma. So now that we have this, consider the other three, combine them together, we would get 1 over alpha, 1 over beta, 1 over gamma. So that is something that you can use. Okay. Okay. Let's see. Let's look at Siva again. So we have 3 points concurrent, 3 lines concurrent. Now, let's say this point over here, well, it's a point, so it has a coordinate, let's say alpha, beta, gamma. Well, now that we've known what happens when you project that point onto BC, it becomes 0, beta, gamma, which means the ratio between these two lengths is going to be gamma, beta, and similarly, it's going to be gamma, alpha. It's going to be alpha, and it's going to be beta. So now Siva's theorem just becomes well, immediate. Gamma over beta, alpha over gamma, beta over alpha, 1. So it becomes an immediate consequence. Yeah, so that's some of the nice benefits you can have for barycentric, to use barycentric. Okay. Mm, let's solve some actual problems first. Let's see if we can look at one. Yeah. Because I haven't thought about like displacement vectors or perpendicular conditions. But let's just see if we can solve one problem. So let's say L is the field of altitude, M is the midpoint of AL, and let's say K is the symmedian point. So K is the symmedian point, Wait, so K somewhere here. Then we'll see if MK bisects BC. Prove that MK bisects BC. Okay, this requires the shoelace formula, but never mind. Let's just see. Okay. There is a collinearity criterion for barycentric, and if you've learned a bit of high school vector geometry, in particular a little bit of high school basic linear algebra, if we have three vectors in 3D space, right? If you have three vectors in 3D space, then they are going to be collinear if they're going to be collinear. These 3 points are collinear if the determinant is 0. Okay, this I think is probably a bit advanced. Never mind actually. Let's try to solve this without determinants, which is definitely possible if we write them all in vector notation in the end. So what we want to prove is M, K, and D. So D is the midpoint of BC. Is collinear. Yeah. So K, we already found that it's A squared, B squared, C squared. And D, we already found is 0, 1, 1. So now we just have to find M and then try to prove that those three things are collinear. So to get M, we have to first find L. And L is the altitude. So how do we get the altitude? Well, it's on the line BC, so we know the first coordinate must be 0. And now let's use ratios again. Yeah, you can use L passes through H. So you can say L is the projection of H. So you can directly say it's tangent B, tangent C. Or if you want to use vectors, then this is you want to use ratios, and it's C. This is C cosine B. This is B. This is B cosine C. So that's gonna be B cosine C, C cosine B, and then use the sine rule so that now you can get sine B over sine C. Sorry, tangent B over tangent C. Alternatively, you can project H to BC. So anyway, L is this. Now, here's the dangerous thing about non-homogenized coordinates. So M here is the midpoint of A and L. M here is the midpoint of A and L. We cannot just take A and L, add them together, divide by 2 if they're non-homogenized, because they are scaled differently, right? We have to make sure they're both homogenized first, and then add together, and then divide by 2. So A is 1, 0, 0. But I want them to be scaled the same way. So let's just scale them so that the scale factor is the same. Tangent B plus tangent C, 0, 0. So now we can add them together and divide by 2. So M is going to be tangent B plus tangent C, tangent, B, tangent C. So yeah, so now we have this, this, and this. Okay, very well. So how do we solve this? So now we have to find, we have to prove that these three things are collinear. So the best we could do is to prove, let's say, uh, KD is parallel to DM. So if we manage to do this, then we're done, right? So let's find KD and let's find DM. So to find KD, it's going to be D minus K. But again, you have to make sure they are scaled the same size first and then subtract. So here, let's scale them. So D, you have to multiply by A squared plus B squared plus C squared over 2. So that would be 0, A squared plus B squared plus C squared over 2. Minus A squared, B squared, C squared. So this is minus A squared minus B squared plus C squared, A squared plus B squared minus C squared. Okay. And now how about MD? So MD is, I'm going to scale them so that it becomes the same. I'm going to multiply by tangent B plus tangent C. E tangent B. Okay, right. So now you want to prove that these two things are parallel. Two things are parallel. Yeah, we subtract. Okay, okay. Right. Yeah. Hang on. Tangent B, tangent C. Let's see if these two are parallel. Are they? A squared plus B squared minus C squared over 2AB is the cosine of C. Okay. AB sine C. Yeah. This. Yeah, we can try scaling down first, but I think we can just write it like this. this is zero, then sorry. If this is zero, then we're done. So this is AC cosine B, tangent B, minus AB. Why isn't D zero half half? Because I used but as I said, you can treat them the same if if they are scaled, if the ratios are the same. Zero half half is the same as 0 1 1, right? Because remember the barycentric condition is that they all add up to one. So if they don't add up to one, then you just automatically know how to make them equal to one. Just divide by some common factor. Yeah. So it's just a simplified notation. Otherwise, we're going to be dividing by a lot of things. But of course, if you're going to talk about the differences, like the difference between two vectors, you have to make sure they have the same scale first. Then you subtract. Yeah. So now here is AB cos C tangent C. This is AC sine B minus AB sine C. Yeah. So this is zero. Exactly. So that means these two are parallel. And this is obviously parallel because they are what? If you notice, these three add up to zero, these three add up to zero. So, so then we're done. So uh, the advantage of barycentric over Cartesian coordinates is that in barycentric, normally the terms are much more symmetric. So you don't get like ugly cases where it's like not very symmetric in terms of A, B, and C. Because sometimes you can get like a result for A, and then you can just say, oh, similarly B, similarly C, which is better. Right? So yeah, you can simplify this note. You can simplify this by if you want to learn Conway, the Conway notation, sure. But well, it's the same thing. It's just simplifying it to a letter. But it's up to you. Because I don't really use Conway. Because well, you can just simplify it like that. So this is one of the applications. But let's not dwell too much on this. Otherwise, it's quite not very advantageous to those who are not familiar with vectors, not comfortable with vectors yet. Okay, now let's just, yeah, so let's do easier sort of vectors. Let's do some sort of easier sort of vectors. So let's say that now I set O as, so this is nothing to do with barycentric anymore. I set the circumcenter O. Previously I said you can set O anywhere, and you can the barycentric won't change. The barycentric coordinate won't change. So now if the circumcenter is O, right, right, I'm gonna make this the origin. Is the origin. So O is zero, it's the zero vector. And for example, the length of OA, the length of OB, the length of OC, they're all equal to R. G, G is still A plus B plus C over 2, over 3, right? Because this you can carry this over right from the barycentric coordinate of G. But again, you don't really need barycentric for this. It's just basic factors. You just take the midpoint of BC and then take A and that equals 0, 2. Then you take this. So G is this. Similarly, you can find H by using the tangent A, tangent B, tangent C thing. But we're not going to do that, right? We're not going to do that. We're going to think of it from what we learned last class. O, G, H. They form a 1 to 2 homotopy. Yeah, so OGH, they form a 1 to 2 homotopy. So H must be just 3 times of G, which is A plus B plus C. Is A plus B plus C. So some of you might be wondering, why doesn't this imply that the barycentric coordinate of H is also 1, 1, 1? Because now it's A plus B plus C. And that's 1, 1, 1. And the reason is, first of all, 1, 1, 1, they don't add up to what? 1 plus 1 plus 1 is not 1. So it's a different expression of H in terms of A, B, and C. Like if you want to use the barycentric one, which is tangent A times A, tangent B times B, and so on. This is still correct, right? This is still correct. The thing about two-dimensional vectors is that if you have 3 vectors, there are many ways to write it in terms of the mixture of those 3 vectors. This barycentric one is independent of the origin you pick. It doesn't matter where O is. This will be true. But this one matters where you put OS. And in this case, we put the origin at the circumcenter. And we can get this nicer form. Right? Right. So now H has a better form if O is the circumcenter. So there's this one fun problem that I can let you guys try. So it's going to be this. Let A, B, C, D be a cyclic quadrilateral. Let HA, HB, HC, HD be the orthocenters of BCD, AB, sorry, ACD, ABD, and ABC respectively. Proof that HA, HB, HC, HD is cyclic. So now we have a cyclic quadrilateral, ABCD, and we can define HA, sorry, it's probably HD. HA is probably here, HB is somewhere here, HC somewhere here. We're going to prove that these 4 things are also cyclic. This one is very hard to angle chase because we don't know the angles between those H's. There are like 4 H's over there. ABD is outside. ABD is obtuse. Where you see? Okay, yeah, true. You have a point. Because I just don't know where the H's are. Okay, if I do it accurately. Let's try and draw HA, HB, HC, HD. So HA is here, HB is around here, HC is obtuse is around here, HD is around here probably. So yeah, they will still be cyclic. No, don't worry. Ram's theorem. Uh, I don't think that will work because we don't really have any information on the angles between like it's very hard to even find, for example, HC, HD, HA. Uh, it's congruent to ABCD. Maybe, I don't know. Well, let's think about it. This is quite a fun problem because turns out, if you change this word, to centroid, the statement is still true. If you change this word to uh wait, yeah, if you change this word to centroid, it's still true as well. Circumcenter, well, circumcenter is obviously true because they're all the same. They're about point. Maybe. Yeah. So what's one way to approach this? We can try to use by this definition, like in this expression for h using vectors. Because now, even though this is not a triangle, but the four triangles ABC, BCD, CDA, and ACB, they share the same circumcenter. So if we let that be the origin, then all of these formulas will work for all four of them, right? They share the same circumcenter. Yeah, so exactly. So if O is the origin, then HA is just B plus C plus D. HB is A plus C plus D. HC is A plus B plus D. And HD is A plus B plus C. So what do we do now? How do we prove that these four vectors form something that is cyclic? Well, I don't need complex bash over here. Again, well, cross ratio is a bit overkill for this. Someone said, well, yeah, the congruency might actually be true. Whether or not it's true, how do we see? Now that we have these four things already. We have these four vectors telling us the positions of those 4 points. plus C plus D, A plus C plus D, A plus B plus D, A plus B plus C. We want to prove that these four are concyclic. What operations can we do to all of them together that will preserve cyclicity? That means proving these four are cyclic just means that proving some other four things are cyclic. Exactly. Yeah. B plus C plus D, A plus C plus D, A plus B plus C, A plus B plus C. If we just subtract this common number called A plus B plus C plus D, then it's just a translation, right? Exactly. So translate by this vector. Then now you're just left with this, which is obviously cyclic. Because this is just the actual points A, B, C, and D. Of course, they're not exactly A, B, C, and D, but they're kind of flipped over the origin. But if you flip something over the origin, it's still cyclic anyway. So exactly, they are congruent. They are congruent, and its orientation is reversed because we did this. There's this minus sign over here, right? It's reversed, and then it's translated by this vector over here. So the same statement is true if you change to centroid, because if you change to centroid, all these four things is just divided by 3. It's just a scale factor of 3. Nothing changes. It's still cyclic, right? Yeah, this is one of the fun problems that I never forget. I never forget. But even though I kind of forgot where it came from. Yeah. So in fact, if you change auto center or even centroid, you can change it to anything on the Euler line, and it will still work because then it will be just a multiple of just a scale, just a scale factor, right? Right. So yeah. Okay. Let's see what else we can do. Let's do a recap, and then we can open up to questions and I don't know, fear some interrogation by you. So the recap here, first of all, we try to actually we already did this recap, sort of try to find cyclic quadrilaterals, try to find homotopy, try to find similarities. Because okay, but you don't want those that are too trivial. You don't want those that you can simply obtain by chasing angles, like just like changing angles here and there. Sometimes you want to. So the reason why cyclic quadrilaterals are so powerful is because if you want to change from this property adding up to 180 degrees, you want to change to this property. It's not that simple by just angle chasing. But if you have this reasoning, which is now that this thing is cyclic, these two angles are the same. You're kind of transitioning from one regime to another without actually adding or subtracting angles. So that's one reason why cyclic quadrilaterals are that powerful. And it also tells you that if you found a cyclic quadrilateral that's non-trivial, you want to exploit this fact, which is you swap between these two properties. You don't want to swap between this property and this property, for example. because these because the red and the green properties are easily obtained without using the fact that they are cyclic, right? So yeah, use symmetry. Uh, Last time Jaheng probably thought about spiral similarity as well. So have that mental picture in mind when you see the angles. Try and see whether there's any similarity between different triangles. And even if there is, try and prove it. Uh yeah, it's just yeah, nothing else to say for the last 8 minutes. Any questions? Spiral similarity, Mikhail point. Yeah, I'm not sure if we talked about Mikhail point. I mean, he probably did. It's still is. It's a cyclic quadrilateral thing anyway. But if I were to recommend a geometry practice book, and Ivan also recommends this, it's something called Geometry of Figures. Oh, wait, let me hang. Geometry in or Geometry of Geometry in Figures. It's a whole book. It's a whole concise book of uh geometry problems that is stated in a very, very simple way. That they're not even words for the questions. They're all just diagrams that intuitively tell you what they're kind of asking. So yeah, it's quite a good book. As in that it's a book without words, but you can practice from those problems, even though there are no solutions. But take some time, you can find the solutions yourself. But convey is hard to some people. Yeah, convey is hard to me. So okay, cool. And I'm not sure. I think this book is free online. It's you don't have to pay for it. Okay. Anything else? So for basic geometry problems, don't rely on advanced techniques. Try and give the most synthetic proof possible. Try to seek for the most synthetic proof possible. Sometimes you can kind of cut corners and use a bit of bashing, but the best solutions are always those that are very concise and short. Right. Um, if not, then we just end here, I guess. So good luck for the test. I have no idea what's on the test, so so don't ask me. But yeah, all right. I'll see you guys soon. Not sure when, but yeah. A plus C, the worst possible combination. That's true. I mean, anything with C is the worst combination. But, okay, so bye.